First, we have done the pre-tension. Now we need to work on the post-tension in the block. In the pre-tension, we have transfer length, a kind of development length, over which the force is going to get transferred from the strands to the concrete beam itself. And here there is no transfer because most likely also there's going to be some debonding between the strands and between the concrete. Therefore, the pre-stressing force is going to be acting as a point load at the end or at the end of the beam, like the end face of the beam. Now, the volume that we'd like here to do analysis and we're interested in is going to have a length equal the same as the beam depth, total depth, which is h. We have here some finite element analysis, and this is actually the output of it. And here is the beam. So the beam itself is like here, if I may mark on this. This is actually the beam, this piece of it. As you see here, the total depth of the beam was 762 millimeters in this model. And the length, we have taken the length slightly larger than the depth. So we have taken it to be 838 millimeters. Just to be able that at that point, at the point of depth h, at 762 millimeters from this face, we're going to have uniform stress. Just to be able to study it in a decent way. We have more than one model. We have one model at which we have a point load right in the middle, in the mid-height, and the other model when we have some eccentricity. In the first model here, we put the point load and then we start to study the stress distribution. The stress that here you are looking at is going to be those stresses in the y direction. If you like to call this to be the x direction, I may call this to be the x direction. And this direction here is going to be the y direction. So the stresses that you're looking here at in this picture, they're going to be all in the y direction, nothing in the x direction, because in the x direction is going to be mostly compressive stresses. If you put compression here, at the beginning we are going to have highly compressive stresses, and in here is going to be kind of uniform. It will become uniform at the end of the beam. At the beginning, the stress was only concentrated in here. This at the beginning. This is where you have the bearing of this end block or the anchorage to the concrete. And then the stress goes from this uniform over a small depth of the beam to the entire beam depth. The stress here, this stress is going to be actually in the x direction, like compressive stresses. Also, this small block that I modeled or I put a box for here, this is going to be also compressive stresses in the x direction. But the stress distribution that here you're looking at is going to be all in the y direction. Right here next to the anchorage, next to this pre-stress anchorage, you're going to see that all the stresses is going to be compressive and is going to be directed in the y direction. And because the stress here is going to have an angle as if it's going to be directed this way, you have a small component here that's going to be seeing some tensile stresses, top and bottom. Of course, we have symmetry about the x-axis. Whatever is happening here on the top is going to be the same as what happened on the bottom. The big tension force is going to be right here in the middle. We call this bursting stress, and this one we quote here spalling stress. So in these two zones is going to be spalling stress zones, and this is going to be the big bursting stress. This is where you have most of the stresses. This is where you start here to put the ties. If I may put the ties here, but of course this is going to be red. The whole thing here is going to be red. So anyways. Now, let me move this point load down a little bit, which means provide some eccentricity. So the distance here from the bottom fibers to the point load is going to be called Y. If you just double it, just double the distance. So whatever, let's say that was here, let's say 10 inches, you just double it, and right there at this height, you're going to see the big bearing stress is going to be surrounded here. As you see here, the tension zone has just been changed from one location to another location. The three areas that we're going to be interested in is going to be this, if I like here to look at this, is going to be the spooling, which means the top and bottom, the bursting, and the compressive stresses. This is going to be the three areas. And also we have three methods of analyzing this end block and finding out the stress and the amount of reinforcement that we need to add in here. Three methods. The first one is called linear elastic. Linear elastic, for example, like this finite element analysis, you can call this linear elastic. If you do statics, like you do, for example, forces, and you try to find out the tensile forces and stresses within the beam, you'd call this linear elastic. There's another method which is recognized by code by the ACI. It's called Stratton time model. There is also another method recognized by the code, the ACI code. It's called approximate method. Both of these two methods are included in the code. So the code has certain equations. He says, or the code says, if you like to do this approximate method, here are my equations. It's kind of this what you call here prescriptive method. But this method is also allowed by the code, provided that this is approved engineering, acceptable engineering method to figure out the stresses and the forces acting on the beam. But the code doesn't have lots of to say on this method. You can just pick any method as long as you're able to do a decent and rational method to find out the forces in the y direction of the beam, like in here, for example. Again, these two methods, prescriptive methods, you have equations for it in the code, and you can just use it from there. When it comes to our project, certainly I'm going to be using this one, approximate method. Also in the final, this is going to be the method to use. These two methods is going to be very important that you understand where they're coming from. Also in your project, you're going to be doing this linear elastic stress analysis. But at the end, when it comes to the design for the reinforcing, you're going to be using this approximate method. So the only reason that we really need to run the analysis with this method here, just to be sure that we know what's going on there and we know how to do the statics of it. It's not really complicated, but we're going to see some example on it today. In the linear elastic and Stratton tie theories, usually, let's say here's the beam, total depth h. This is going to be the end block that we're going to be working on of the entire beam. If the beam depth is h, we're going to be doing this general zone that we're going to be studying is going to have a length of also the same as h. It's kind of like when you look at the stress distribution, you're going to say, well, distribution is going to be like a 1-to-1. So this is going to be the general zone that we'd like to study. If you have the pre-stressing anchors, it's going to be kind of eccentric, which means not right in the middle height. You can take here this zone, and we're going to call this to be the local zone. So if you like, I can also take another zone, which is going to be this zone here. I'm just extrapolating the discussion. I can say this looks like a piece of the beam that also I may just focus the stress analysis and the study just to limit it to this zone here. This is going to be the very local zone, and you may call this the local zone for two anchors. This is going to be the general zone for the entire beam. For each one of these zones, you should be able to work and do some analysis and find out the amount of tensile stresses in the y direction, not in the x direction. Because remember, when you put the ties, you're going to put it in the vertical direction because you're going to have tensile forces in the y direction. If you look here at the local zone, this is here a picture of the anchor for post tension. Here's a strand, 7-wire strand. And then here I have, as you see here, 1, 2, 3, and 4 wire strands. In this 4-wire strands, the whole thing here is going to be embedded in the form. Then after you cast the concrete, this plate here is going to be bearing on the end of the beam. And this piece is going to be sticking out. And this sleeve or this duct is going to be just continuous. It doesn't stop here. It just cut to show us what's happening inside. But this duct here is just continuous. It is very similar to the electrical conduit. I'm sure that you guys have seen some flex electrical conduit. It looks like this. This is made out of aluminum because it needs to be very light. It's not steel like in electrical conduit. And then you have the strands inside it. When you have here the pre-stressing forces, it's going to be bearing on this plate. So this plate here is going to be bearing on the concrete. And this cable that you see, or this wire, this tie, if you like, called the spiral tie, it is to resist the tensile stresses in the local zone. So right here in the local zone, you're going to have this tie, the spiral tie, and the job of the spiral tie is to resist the local tensile stresses. So the big tie that I'm going to put here, the beam, is to resist the stresses in the general zone. But when it comes to this very local zone, we're going to be using this spiral that comes with this bearing. It comes with the anchorage. Any questions? We're good? All right. Now look at this end block. Look what happened to the stresses when you have this eccentricity. Because if you put the point load in the middle, like in this case, in all of these cases, we're going to have the force, the compressive force is going to be coming this way. It's going to be the mid height of the beam. Same thing here, right? Same thing here. After a distance, which is equal to h, look at this. Here's h, here's h. It's going to be the area of study. The stress is going to be completely uniform. It's going to be equal. But if I may go back here one slide, when you have some eccentricity, stress distribution is going to look like this. Just in general. It's going to look like trapezoidal distribution. Difference is in here, the point load is going to be right in the mid height. And in here, the point load is going to be centric loading. Therefore, you're going to have here more stresses than this side. If you have lots of eccentricity, you may end up with a situation like this. But if you have less eccentricity, at certain point, once you bring this 2-point load in the mid height, your stress distribution is going to be completely uniform. So it depends on the amount of eccentricity this lobe is going to be happening, and you may end up with some maybe tension at the bottom and compression on the top. Now let's study all of these cases and see what's happening. The stresses that you're looking here at, the red ones, the dashed ones, is going to be compression, and this is going to be the stresses in the X direction. So all of this red dashed lines, it is going to be the stresses in the X direction. This is going to be the X direction. At the beginning, it's going to be concentrated in a smaller area, and once you get close here after one edge, it's going to be completely uniform for the entire cross-section area of the beam. This solid lines that here you're looking at is going to be the tensile stresses in the Y direction. So compression is going to be dashed, and the solid is going to be tension in the Y, but the compression is going to be in the X direction. Most of the stresses for the tensile stresses going to be localized right here, which is going to be creating a kind of some tension force right here. If you like, I can just draw it here. It's going to be in both directions. It's going to be going up and down. If you take the same point load and put in the beam, I'm going to be going here to the top model, top illustration. Since this is going to be uniform, I can just take this uniform stress block, divide this into two segments. See, the top piece here, the top stress and the bottom stress distribution, I can just find out the resultant, which is going to be P over 2. It is going to be at quarter from the head top of the beam and quarter from the bottom of the beam. It's going to be P over 2 and P over 2. I can just draw this straight line, which is this dashed line here and there. And then at a certain point, I'm going to say now where the tension is going to happen. I need to have some advice. Let's say tension is going to happen about in this location. If tension is going to happen at this point, this straight line is going to stop here, and then another force. So I'm going to have here a force coming this way, which is P over 2. And this force here, of course, I should be able to find out the resultant, because I'm going to have here this point load P is going to be divided into two forces. And then at this joint here, if you know how to do truss analysis, like method of joints, you should be able to find out the force that goes up in this direction, like in the Y direction, which is going to be this tension force. So if you can do joint analysis, exactly the same one that you have done in statics for truss analysis, you should be able to find out this tension force T. You're going to have also another force going down, which is also going to be this force T. You'll find out that this location of the force T is going to be almost same location as this. So whether you're going to be doing finite element analysis, find out the stresses, or you do this model, which is called the stratal time model, you'll end up with almost the same location of the force. Maybe values of the tension force is going to be a little bit different. It depends on the method that you're using, but location is going to be almost the same. Now, if you look here at this stress distribution, this is going to be the stress distribution in the Y direction. If I may take you back here to one of the slides that we looked at earlier in here, I have here some compression, and this compression actually is going to be in the X direction, in the Y direction, and this tension is going to be in the X direction, in the Y direction also. Excuse me. All the stresses that you're looking here at in this slide is going to be all in the Y direction. So in here, this is going to be tension. And in here, you're going to have some compression. And these two forces needs to be equal to each other. Moving here forward. So again, if you like to do here finite element analysis, take this model, and this give you all the stresses in the Y direction. This give you the stresses in the X direction. We call this the bearing stress. This can be all compressive stresses. Look at the compressive stresses, just goes up and up, right? And then it's get here more uniform. At the beginning, it was just localized, and then at this point here, the stress is uniform. Very similar to what we have done here in this stress distribution. But in here, this give you all the forces and tension forces and stresses. This give you the bursting, and this give you the spalling. We a little bit of tension in here, and a little bit of tension here. Then we're gonna have here some compression. So here's gonna be some compression forces here. If you like to do some elastic analysis, you can also end up with the same distribution that you're looking here at. Look in the middle. This contour line is going to be referring to the highest stress. And then it just goes down and down once you get away from this point. You see it goes down this way and also it goes down this way. And at a certain point, you're going to have here zero stress. And then you're going to start to flip into or going into the compressive stress. This here explains the stress distribution in the y direction. This means I'm going to have here a tension force in this location and compression force in this location. It looks like a couple because I have here two forces equal to each other, opposite to each other, and they're creating a little bit of a moment. At one point, we need to figure out what's happening here. I mean, how can we figure this out? How can we solve for it? Now, with this linear elastic theory, which we're using here, I can come up and put some tension force in this location and some compression force in this location. And the question is, how much is the distance between this tension force to compression force? Because if this T is going to be equal to C, you're going to say there's some moment which is equal to C or T multiplied by the distance between the two. My goal at the end is to figure out the tension force. So there's going to be some moment that I need to figure out. Once I have this moment, I can divide it by the distance from the C to the T. This distance here, the moment R. But first, I need to find out the moment and then find a way to locate the tension force and compression force. You can do the same study in the local zone if you want to. So if the force here is going to be right in the middle, you can just take the block on the same beam, and let's say here's a beam, let's say 9 units. I can just go here 9 units and study this in the block. But if I'm going to do here eccentricity, this can be kind of local zone. They can study the whole thing again in this local zone. Here in this slide just tells you that there's going to be 3 zones. The first zone is going to be this compressive zone. It's going to be right below the plate, the anchorage plate. Give you the big bursting, and then you have the spalling in both sides, top and bottom. Now, in order for you to understand this and to do your analysis, you need to look at the stress distribution. You put here a point load, and instead of having a uniform stress for the entire depth, you're going to have here more compression and maybe some tension is going to happen here. I'm going to go back here a few slides and remind you with this slide that we discussed the stress distribution. When I put here the consultant point load, the anchorage is going to be right here at this location, right in between these 2 point loads. You're going to have here more compression forces and stresses. When you have more eccentricity, instead of having uniform, so at the beginning, you have just uniform stress, you're going to be moving the load up, creating more eccentricity, and then at certain point, you're going to start here to have some tension, and this is exact same thing that you're looking here at. I brought here some eccentricity, I brought the point load down. What happened? I start here to have some tension, therefore this is going to be here compression. I'm going to put here C for it, and here I'm going to have some tensile stresses and tensile forces. So I'm looking here at this compression and tension force and try to figure out a way of finding out this moment. But once I put the force here right here at this location, this is going to be the pre-stressing force, I should be able to find out the stress distribution. Because if this is going to be the center line of the beam, the mid height of the beam, right? Let's say about here. I know that I'm going to have here some eccentricity. So I'm going to have P and E. And at the distance of H, which is about here, I should be able to find out the stress distribution with the two equations I have. I have one equation for the stress in the top, another one for the stress on the bottom, and therefore, I should be able to find out the stress distribution. So this force is going to be given because you need to design for it. Based on this force and location, you should be able to find out the stress distribution on the beam. In some analysis, you may end up with compression here, very high compressive stresses, and some compression on the top, or maybe some compression, some tension. This is as if you have a beam. Now, where is my beam that I need to do here for the analysis? I'm going to say, here's my beam. Here's the span of my beam. I may take it out here, just for sake of discussion. Here's my beam. The type of forces that I have on this beam, I'm going to have here a point load, this location. And I have here some stress distribution on it. So I'm going to say stress distribution is going to be something like this, which is the stress distribution. I just took them out. I moved it here for this location, and I move also this here for this location. So it's going to be a set of forces, right? I'm going to have here some force acting on it and some stress distribution. So I was going to say, we are used to see a beam like this with two supports, simply supported beam. Right? This is going to be like the standard beam that we are used to. But there's also this type of beam. This beam is in equilibrium. Meaning, if you do the stress distribution here, if you do the integration for it, find out the forces, you're going to end up with a balanced system. Meaning, I'm going to have here some compression force is going to be coming this way. Some tension force is going to be coming this way for the stress distribution. And if you like to take the three forces, add them to each other, you're going to end up with a zero force. They need to be in equilibrium. So what you need to do here, if you like to do some analysis, is to start to split this is stress distribution into very small segments. You see, here's one segment from here, right? You see, this is going to be my segment. And for that, you're going to have a force here. You can do integration only for this section. So now I'm going to have force coming this direction. Do the same thing for this segment. Do another force here. Same thing, do another force here. You just continue. You're going to fill it with lots of forces. So instead of having a stress distribution, I'm going to have here a bunch of forces. How to find out this force? You just take the stress at this point, if I may enlarge, zoom in. The stress here at point 1 plus the stress at point 2, divide by 2, get you an average, then multiply by the distance from this point to that point, times the width. With that, you're going to have one force. So at the end of the day, you're going to have a bunch of forces for the stress distribution, and the pre-stressing force is going to be coming this way. For this type of forces, you should be able to find out the moment distribution on this beam. And here is the moment distribution on the beam that you're talking about. Here we go. So what is this moment diagram? This moment diagram is going to be based on this pre-stressing force and all the reaction coming to it from the stress distribution at the end of the beam. There is a method to figure out this moment, numerical method. We're going to create a table, and in this table, we're going to be doing the moment. We're going to be taking sections and just draw this moment diagram. After you draw this moment diagram, you can just take the maximum moment. Where's the maximum moment? Because it's going to be right here. This maximum moment is resolved into a couple. We have here a compression force and a tension force. And this M max, this moment, is going to be equal to this tension force. Let's say M equals tension force times what? Times the distance. This is going to be h. You see this h? Minus x. H minus x. Let me remove this x. This is actually the multiplier. So it's going to be the tension force multiplied by the distance from here to there. This distance is going to be equal to h subtracting x. So I guess with the given information, pre-stress and force, eccentricity, I was able to draw the stress distribution. And based on this, I was able to do the moment, take the maximum moment. That was step number 1, put the point load, develop the stress distribution. Step number 2, draw the moment diagram. Step number 3, identify the maximum moment. I'm going to say, here's the maximum moment. Yes, I know it. Right? Following step, figure out the location for these two forces. Location of C, this compressive force, is going to be at H. Location of T is going to be at X. If someone's going to give me here H and X, I'm going to say the moment is going to be equal to one of these forces, tension force, times H minus X. So now I have the moment, I have H minus X. I should be able to solve for the tension force. This is in general the steps that we're going to be doing. Here's the equation. Here's M max, right? Is going to be equal to the tension force multiplied by H minus X. Once you find out this tension force, what do? You divide this by Fs, and Fs is going to be limited to 20 psi. Just control the crack. Now, in order for you to use the ACI, you need to have load factors. If you remember in any concrete design, we do load factors. This can be here an actual design. This is not a service check. For example, when you're doing here the beam design, the pre-stress beam design, we do capacity design, which means Phi needs to be larger than M sub U. But also at the same time, we used to do lots of checks. This checks is going to be for serviceability of the beam itself. We did stress check right after transfer, just to be sure that the beam is not going to be collapsing under this high compressive stresses, under some tension, and also we did it through the service line. But when it comes to actual design or capacity design, we need to say phi main is going to be more than M sub U. Same thing here for the bearing. How can you design the bearing? How you design the reinforcing? It needs to be stress design. Your load factor here is going to be equal to 1.2. If you remember, we used to say 1.2 dead load plus 1.6 live load. Now it's going to be pre-stressing force. And for the end block design, you're going to be using a load factor of 1.2. This is actually what we're going to be doing. When it comes to the amount of pre-stress that you need to design for, we're going to be going through this once we come to close to an example. It's going to be 70% of FPU. The 270, you take 70% of it. Again, this gives you the local zone, and this gives you the general zone. And you'd like to see this approximate method, and how can we use it? Here's the stratum tie again. If you have one force, you can divide it here into two forces. It depends on the plate size. And the first time when I discussed this, I just considered that the plate size can be equal to 0. Let me take you back to this slide. When we did the analysis this way, we said, well, this can be just point load. But the reality is, you have an anchor plate. And this anchor plate is just distributing the stresses on the face of the beam. Here's the anchor plate length. It has a length. This is why you just take 1/2 of P and put it on the top, put it on the bottom, so your angle is going to be slightly different. When you put a bigger plate, what's going to happen? Let me start here by putting a plate. Let's say the plate at the end is very small. It's going to be like this. Therefore, the location of both of these two forces is going to be close to each other. If I assume that this plate has a zero height, almost the height is like half an inch or nothing, there's going to be a 0 point. There's going to be 1 point load. This is going to be P. When you put a bigger plate, let's say I'm just exaggerating here, put a bigger plate for bearing, what's going to happen? The location of this force is going to be pushed up. So instead of having it here, it's going to be about here. If you put the plate to be the same size as a beam, like this, what's going to happen? You're going to end up with the point load right at the mid height. It's going to be aligned with this force. And you're not going to have any tensile stresses or tensile forces. Therefore, if I put here a big steel plate to have the same depth, the same cross-section area of the beam, you're going to end up with no tension force. If I start here to reduce this plate size, I'm going to be creating more tension stresses and more tension force right here at this location. If I put it to be extremely small, what happens to the tension force developed there? And this is going to show that this tension force is going to get larger and larger. So again, location of this force here is going to be controlled by taking 1/2 of the force, which means 1/2 of the height. And again here, 1/2 of the height of the beam, of course, the beam total depth, and put a point load right in the middle in both of these two cases and come up with this location here. So the location in a beam like this is going to be controlled by simple analysis. Unless I have a different situation. Let's say here's a beam. I'm going to put here some blocks on the top and the bottom. What happens? Look what happened here. Location of the force here is going to be controlled by location of the pre-stress I'm going to be putting there. Let's look at this case. Here's the point load. A bearing plate is going to be that big. It's going to be slightly larger. It's going to be like here. Stress distribution is going to happen so that this point here is going to be at 1/4 of an inch from the top, this 1/4 of an inch from the bottom. You go here h/2, and then you draw your lines. You have a force coming this way, and a force coming that way. Once they meet, it's going to be a component that's going to be providing tension in this direction. Unless you have a beam that is completely solid at the end block, and right after this, it's going to look like an I shape. When you have an I shape like this means that you are pushing and controlling the force on the top to be in the flange, and most of the force also to be in the flange. There's going to be some little bit of a force in the web. This is going to be here the beam web, but most of the force is going to be on the flange. So here you're controlling the location of the force, you just push the top. So in beams like this, when you have an I shape, I'm expecting here to have more tensile force. Because look at the slope of this line compared to the slope of this line. What happened here when I have an I shape, I push the force, the compression force, to be more into the flange. Because I cut lots of concrete from the middle here. I just created a thin web. And here I have completely rectangular force, rectangular beam. And I'm gonna have here rectangular, I'm gonna have uniform stresses on it. But in here it's gonna be different. The force is gonna be pushed up and pushed down. This is the reason when you have an I shape like this, you come here at the end of it and you provide a solid piece of concrete to reduce the amount of stresses and forces on it. The approximate method is so simple. You just say, here is a compressive force. Of course, you're going to have some eccentricity. Here's the stress distribution. It's going to be right here, right? What you need to do is to find out the distance from the top to the center of the anchor. And this distance here, you're going to be using it to be exactly same as D of the bearing, location of the bearing force, which means tension force is going to be happening at the distance equals to the distance from the point load to the top, to the closest top or bottom of the beam. Let's look here at the equation. Equation says the amount of tension force that you're going to be designing your reinforcing for is going to be equal to quarter of summation of all the forces that you apply at the end of the beam. In some cases, you have a couple of anchors, right? Maybe you have 3 anchors. It happens. We're going to have here 3 plates. It's going to be also here. And each one of them is going to have a force. So you can have here few forces. And what you need to do is just add all of these forces, right? The 3 forces, all the pre-stressing forces, multiplied by the following. 1 minus the height of the anchor divided by the total height of the beam. If you want to be conservative, you just take the anchor height to be equal to 0. So in some cases, we say, well, height of this anchor is going to be equal to 0. And in this case, this term is going to vanish. It's going to be just, instead of having a reduction, this term is going to be equal to 1.0. So the code equation is so simple. It just says take quarter of the total force applied at the end block, which means the pre-stressing force, and use to be your tension force for the design. Where is going to be located at? Take this amount of eccentricity, if you like, call it eccentricity from the top of the beam and just reflect it in the x direction. This give you your location for the tension force. And this is where you design your reinforcing for. So if I have 400 kips as pre-stressing force, roughly I can say I can just take quarter of it. It's going to be like 100 kips, design the ties for. I say, well, this quarter is a lot. Anyone recalls what was that percentage of the pre-stressing force that we have used in the pre-tension anchor design? Was it like 10%? 20%? Anyone remembers the value or the ratio? Yes? In recollection, rough estimate? Here's the one that we have done for pre-tension. Slide set 9-1. Let's see what was the approximate value that we have used. How much was it? Can you guys read this for quick? Equation says take about 2%. That's it. You just take 2% for pre-tension. But when it comes to the post-tension, we're talking about 25%. There's a big difference here from 2% to 25%. You can compare. What is the big difference between the two systems? In one system, if you guys recall, I have the point load right here. Transfer of the force is going to be happening within the beam itself because you're going to have this development length because you have the bond between the strand and between the concrete. And at the case like this, for the pre-tension, I have only the force, tension force is going to be only 2%. And here, I have the point load completely out. It's going to be like this. Put all the point load completely out. There's no bond between the concrete and between the strands. And therefore, the amount of tension force that I need to design for jumped to 25%. This is a lot when you compare to 2%. So I'm expecting if I'm going to be buying an element from a factory like pre-stressed element, the amount of reinforcing needed there for the anchor is going to be very small compared to that if you like to do it at the site. If you like to do post-tension, what does it mean by post-tension? It means you cast the concrete first, and then after you cast it, you start to apply the pre-stressing. This usually happens at the site. You should expect that you're going to have some issues here with the anchor. While the one that you do it in the fabrication yard in the factory, you're not going to have lots of reinforcing for the end block. End block is not a big deal. It's not very critical. But when you do here post-tension, end block is going to be very critical. This is the conclusion. Any questions? I'm waiting for questions.
Yeah, so I do have a question. When you were talking about the 2% and 25%, what was that a percentage of?
Of what?
You were talking about 2% for the pre-tensioned and 25% of the post-tensioned. I was
Yeah.
asking, what is that a percentage of?
Percentage of the pre-stressing force.
Okay, thank you.
So we take 25% versus 2% of the pre-stressing force, and then we use it to design the ties. The ties, of course, is going to be in the y direction, if you like to call it the y direction, right? Meaning I'm expecting lots of ties to happen in post-tension beams versus pre-tension beams.
Got it. Thank you.
No problem. Thank you. Now the following slide set to continue. Same slide set that we have in the previous. Same slide that we have in the previous slide set. The amount of tension force is going to be 25% of the total force applied on the anchor. You can reduce it a little bit with this factor, and this reduction is because it's going to be the size of the plate. If you have bigger plate, you're going to have more reduction. If you assume that you're going to have here zero height of the plate, you're going to have 25% of the total force. This equation makes sense because what happens if I'm going to add here a plate that has the exact height as the beam? Here's my plate. Now the height of the anchor, H anchor, which means the height of this plate, is going to be the same as H. So it's going to be this term here is going to be equal to 0. And this makes sense because if you put here a very big plate, it means all the stress is going to be going straight, no eccentricity, no tension force. You don't need any ties. But it's not going to happen because this plate is just expensive. Especially that if you want to really eliminate all the tension forces, you need to go with a very thick plate to be sure that it's going to be a rigid plate and the plate itself is not going to be deflecting or deforming and provide complete uniform stresses on the end of the beam. So it's going to be a cost. Plate is going to be heavy. You don't want to do this. Now, this location, the deep bursting deep, is going to be this distance from here to there is going to be the same as the distance in the x direction for the location of the ties. In this slide here, just repeating the same equation and just give you definition here. What does it mean by summation of P sub PU and H of the anchor? How can you figure it out? Again, definition for the eccentricity, how it is done. Now, the Ashley and Caltrans, when it comes to bridges, they say this is not going to be the only force that you're going to be designing for. And here's the reason. They say most likely this anchor is going to come here on an angle. And this tension force here, again, or this pre-stressing force, is going to be coming with an angle of alpha. And this can be creating additional force in the y direction that needs to be added to the design force for the reinforcing, for the tire reinforcing. If you take the component here in the x direction, it's going to be P cosine alpha, and the y direction is going to be P sine alpha. So what Ashton and Catron say in their design specifications, they say this tension force, you take it the same from the ACI equation, and then you add to it this term. You're going to be taking this P sine alpha. You need to be added there. Now, someone's going to say, is it going to be completely PP sub U sine alpha or half of it? Why should I take only half of it? Can you guys help me with that? Can someone help and answer this question? Yes? All right. Let me discuss this with you guys. When you look here at this force, PP sub U, you take this component and then you're maybe taking also this component. This component is based on one half of this force. And this component here is going to be also one half of this force. So this tension force here is going to be this component in this direction based on this given angle and also based on only, we're going to say here, P over 2. So when it comes to putting any force here with an angle, you need to understand that both of these two components, one is going to be going to the top, one is going to be going to the bottom. Therefore, this is the reason that you are be taking here half of the force times sine alpha. Because one half is going to be going this side, the other half is going to be coming this side. Now you need to factor the loads. Your design compressive stress, you need to factor it. As I said here, the load factor is going to be equal to 1.2 when it comes to bearing. Here's a snapshot of the code of that section. And it says this 1.2 here is going to be your load factor. And you're going to be using 80% of FPU. If FPU is going to be 270, you take 80% of it, multiply by 1.2 times APS, end up with this equation here. 80% of FPU is going to be 216 times the cross-section area of APS. Therefore, you end up with this equation. And then it says here the factor pre-stressing force that you're going to be using in the anchor design. It's going to be the force that you use here in this equation, right? Is going to be equal to the least of A through C, which means I need to try this equation, try this equation, try this equation. At the end, I'm going to be taking the smaller of all of them. The first one here, it says take 94% of FPY. But I know that I have this relationship between FPY and FPU. FPU is going to be the 270. FPY is going to be 85% of it. How do I know that? Because I know it from the code table. Let me just go forward quick, and I'm going to come back to the same slide. Here we go. For stress relief strains, the ratio between FPY to FPU is actually equals to 85%. So the reason that they give more than one equation, because in some cases, FPY divided by FPU can be 80% or maybe 90%. So in this case here, it says times FPY. In this case, it's going to be times FPU. It just happened when I'm using 85% that I end up with the same equation. So for the type of strands that we are using the 416, these two equations will yield the same force. But in a case like 722, you may end up with two different equations, two different values, and you can just take the smaller of the two. Same thing here when you have 90%. So this can give you here the factor design load. And this factor design load, what you need to do take it to this equation, add up all of this compressive forces based on this selection, multiply by 1.2, right? And here. And then after that, you take 25% of it, and this is going to be your tension force. If you like to reduce it because the anchor height or the plate height at the anchor, this is fine. You can reduce it. In many cases, we just take each anchor equal to 0 and use just 25% of the total compressive force to design the ties in the y direction. Is it okay? The phi factor, since I'm going to be doing here strength design, I'm going to have a demand, and also I need to have this capacity. Demand is coming from this equation. It's going to give you here the demand, right? And then you take 25% of it. The phi factor for bearing, for the anchor zone, is going to be equal to 0.85. It's going to be constant. Take it from this table. In the code for the phi factor, just take 0.85 and that's it. This should be fine. Just one value, very similar to the shear thing. The shear is 0.75, and here the post tension is going to be 0.85. All right. So I'm going to have here more than one check when it comes to design according to the code. The first one is going to be the bearing stress. You understand when you have this bearing, and this bearing is going to happen in early stage of the pre-stressing, the actual bearing stress that you're going to be doing is going to be equal to FPU divided by the contact area between the plate and between the concrete. The maximum allowable area in this case, FB max, which means this is going to be FB max, is going to be equal to 0.7 times F prime C square root of A divided by AG. What is this A divided by AG? A divided by AG is because you have this confinement around the concrete. I'm going to go back here to one of these pictures. The contact area between the plate and the concrete is not the total area that would see all the compression force. Example. If I take here this area here, right? You're going to say, put a plate with this total height. So area of the plate is going to be the same as the area of the cross-section area of the entire beam. In a case like this, there is no confinement coming from the concrete to help in bearing. If you may want to go here and look at the equation, you can say, yeah, A now becomes same as A sub G. A sub G is giving the total area of the plate, the gross area of the bearing plate. And A is giving the area, let's say, of the beam, just to make it simple. Cross-section area of the beam. When both of these two areas is going to be the same, right, this is going to be equal to 1. If the area of the plate is going to be smaller than this A, it means this factor here is going to be large. And this factor here, it has a maximum limit that you can use. And this limit would give you this equation here. This factor usually, if you guys have done any paste plate design, steel plate design, this factor is going to have a maximum value of 2. Beyond 2, you can't really use it. Also, the maximum bearing stress, it's going to be within 2.25 square root of F prime C. It seems to me that this factor is going to be controlling your design, because if this is going to be a maximum of 2 times 0.7 is going to be 1.4, smaller than 2.25. So most likely this is going to be the factor that controls your design. Let's see here an example and how can we do it in this example. This is the same beam that we have done, example 7.1. Same properties, same number of strands, same concrete strength, same strands that we use, 270. Same depth, the exact same example. But what I'd like to do here, I'd like to do a design for the end block using the following 3 methods: linear elastic stress analysis, classic strut and tie method. And of course, I'd like to see what does mean by this approximate method. How does it compare? Because approximate method, you're going to be doing it here in a second. It doesn't take any time from you. So in this beam here, if you remember, I have 13 strands. And the 13 strands, they're distributed like this. If I may go back here, I'm just trying to find out. Okay, let's just stay with this. Here's the bottom of the beam. I'm going to have 5 strands. This is going to be 5. This is going to be 5 strands. This is going to be 3 strands. You see here, I'm going to have 5 strands to be right here. Additional 5 strands. Lastly, I'm going to have here 3 strands. As it says here, here's the first row. You're going to have 5 strands at the bottom. Second row. Third row is going to be only 3 strands. Location of the strands here, I can design it. So I'm going to say here, from the bottom, I'm going to go here 2.5 inches. What's after that? 4.5 for the spacing. So 2 plus 4.5 is going to be 7 inches. Plus 4.5 is going to be 11.5 inches. So actually, this dimension provided is going to be the location from the bottom of the beam. So okay. The total force applied right here is going to be based on 13 strands. Location of this force here as a resultant is going to be towards the bottom. Because if I end up with 5, 5, and 5, my resultant would have been right in the mid-height. Because I have 5, 5, and 3, this resultant is going to be pushed down a little bit. How do you find the application of the resultant? The easy way to take the moment about this point here. Take the moment about this. For what? For all the forces. And then you say it's going to be equal to the moment developed by the resultant. The amount of force that I have in 3 strands is going to be equal to 118,973, and this is going to be for 5 strands. It's going to be also for 5 strands. So someone can take the moment about this point for all the forces and just cancel this one. Or maybe according to what we are doing here, you can just take the moment about this point, about the bottom. So first, the moment due to the strength. So I'm going to have here 5, which is 198. So instead of saying 198, I can just simplify it, say 5 strands. Because it's going to be 5 times F for 1 strand. It's going to be also 5 times F for 1 strand. 3 times F for 1 strand. So you can just say 5 times 2.5, like what you're looking here at, plus the next 5 strands times 7 inches. 7 inches, 2.5 plus 4.5 is 5 times 7 inches. Plus, that's 3 times 11.5 inches. Where is 11.5? I'm going to say 11.5 is going to be from here to there, right? So this term here is going to be the moment, if you like. This is going to be all the moment, right? Due to the pre-stressing strands. The other moment that I have here is going to be coming from the resultant times the location of the resultant from the bottom of the beam. Let's see, this distance here, how much is that? This is what I'm looking for. You can call this E if you like. This amount of eccentricity, this is what I'm trying to get to. So I'm going to say this moment is going to be equal to 13 strands because I know that this R is going to be equal to 13. If this force is 5, 5, and 3, total force is going to be equal to 13. So it's 13 times eccentricity. Set them equal to each other. Or what you can do, take the moment due to the strands, divide by 13, which the resultant is going to give you this E. So actually, this value is going to be my E to eccentricity. Location of the resultant force from the bottom of the beam. It's going to be this guy here. Any questions? Yes? Any questions on finding out the eccentricity? Yes?
How
Everything is
did
good? Yeah.
the number of strands in each force, was that given for the problem, or did you decide how to divide up the strands in your design?
If you remember that this problem here that we solved it before already, right? And in this example, it was solved in previous slide set and lectures. And while we were doing the analysis, we decided that we're going to go here with 13 strands. So in our case here, this is now given to us because we designed the beam already for the amount of strands. And what we're trying to do here is to design the end block. Does it make sense?
It does, thank you.
Okay, no problem. Yes, Emilio, what is the question? Yes, distance taken from the bottom. Here's the bottom of the beam. Someone's going to say here, how did you come up with 2.5 inches? 4.5 inches, 4.5 inches. I'm going to say also for the previous example. This is according to our design. So in this case, for this specific problem, it's going to be given to us. Same as number of strands, the size and the amount of force, this is going to be all given to us. So I have been given 13 strands with this distribution and with this location, but the resultant was not given to me. So in this, my task here is to find out the resultant location. Eccentricity, how much is that? And eccentricity, based on this analysis, turned to be about 6.35 inches, which is this red arrow, this dimension from here to there, from the bottom of the beam. All right. So here's the location. It's going to be right in the middle. Big jacking force is going to be right here. Okay. The big force is going to be coming right here. Here's the CG of the beam at 18.84. Someone's going to say, where did you get this from? I'm going to say, okay, simply go here. This is going to be the C to the bottom. You see this? 18.84. Location from the centroid to the bottom of the beam is going to be 18.84. So here's 18.84 to the CG, the centroid. Strands is going to be at 6.35. Therefore, the distance from the strand to the CG is going to be 12.49. And this 12.49 is going to be actually the eccentricity that you need to use in your analysis to find out the stress distribution, because the force is going to be concentrated here. Now, this shows you here, when you have plenty of strands and you'd like to distribute them, but you're not planning to make them as uniform. For example, when we did the double T, we decided that we're going to go there with 4 strands in each leg or web, right? We said that we're going to have 8 strands, correct? Anyone recall the 8 strands in double T? In your midterm? The example? When I have here 4, I'm just assuming to be at one location. But it's going to be so important that when I detail the beam for my design, that I put them so that the centroid or the resultant of this 4 strands to be right at the location so that E is going to be the same as I have considered my analysis. In this case here, I have 13 strands. How can I distribute 13 strands? So what I start to say, I need to put them 3 rows. I cannot put them in 2 rows. It's going to be fully congested. So I decided here to put 5, 5, and 3. So resultant now is going to be shifted a little bit. And actually the distance from the centroid of the beam to the resultant location is actually what I call here E. How this is determined? I have y to the bottom, 18.84, subtracting 6.35 is going to be 12.49, which is my E in the analysis. I really care about this because when I do the stress distribution throughout the depth of the beam, I need this number here. I'm gonna use here this equation. If you remember, my equation for F top is gonna be equal to Pi divided by the area of the concrete. So I'm gonna say, where is this Pi coming from? I'm gonna say this Pi is coming from addition of the three forces. How about area of the concrete? I'm gonna say coming from here. Look at AC, 377. So okay, here's total force divided by 377, because now I consider the total force to be right in the middle at 6.35. Now this becomes here 12.49 is becoming the interesting. So I'm going to say 1 minus, and then I have E sub C sub T. Here's E, the 12.49. C sub T is going to be this, 21.16. If you ask me this question, where is this coming from, I can just go simply to slide number 10, and it has Y top, or C top. They quote here C top, 21.16. Bottom is 18.84, to the top is going to be 21.16. Take this 21.16 to be your Y to the top, right? Divided by R squared, also taken from the properties for this section. I'm gonna have a stress here of 409 psi is gonna be tension. So the stress here, as you see in the distribution, is gonna be 409 as tension stress. Any questions? Yes? No questions? Okay. How about the bottom stress? Let me figure this out. Can use the equation for the bottom stress. Very similar equation. I guess you guys are now masters of these equations. We have total Pi divided by AC, 1 plus. Here it was 1 minus. 1 plus. Eccentricity, 12.49. C to the bottom, the 18.84. Divide by R squared. I'm getting here negative 2250 psi. Look at this. Yeah. So with that, I was able to find out the stress distribution. From the top, it's going to be 409, and the bottom is going to be 2250. And this give me the three numbers I have. 1, 2, and I have the force and the location. My goal is to find out this moment distribution. If you recall, there's a way of doing this moment. Take the maximum moment. You remember taking the maximum moment? I need to take some maximum moment. I have here a moment value in this case. I have another moment here. Take the maximum of the two. And then after that, try to find out the tension force that we were talking about to design the ties. So right now, what I was able to do, find out the location of this resultant force, the pre-stressing, do the stress distribution, but I see here lots of numbers that I don't know what is that for. This is what I need to work on to find out the moment distribution. So first, I'm gonna be cutting this total depth of 40 inches into segments. Each one of them is gonna have a height of 4 inches. You guys see my screen? Yes?
Yes.
All right.
Yes.
Here's the first 4 inches. So the height from the bottom here is 0, all the way at the bottom. Height is gonna be 4, 8, 12. All right. How many segments do I have? 40 divided by 4 is gonna be 10, right? 10 pieces. Okay, good. Just got me in 2 pieces, 10 pieces. How about this dimension here? It says here 2 inches. Say, oh, this 2 inches here is going to be the mid height of this segment. Mid height of 4 inches is going to be at 2. Mid height of between 20 and 16 is going to be at 18. Mid height between 28 and 24 is going to be 26, right? But when it comes here to location of this 6.35, look at this. I'm going to put it right there. Instead of going to 6, just going to be going here to 6.35, just to make my numbers easier. Okay. At each height, let's say this is going to be the mid height of this strip or segment. I need to find out the stress. So what are these numbers in the middle? It's going to be the stresses. Where at is going to be at this line, not this one. It's going to be at this line here. So this one here refers to, if you'd like to take a note, 2117, right? It's going to be to where? It is going to be to this guy here that I put the line on. The stress for this one here. How can we do the stress here? I'm going to say this is going to be simple by interpolation. If you know here's going to be 2250 and here's going to be 409, I can find out the slope. Take the slope, right? And start to come up with the stress at each mid height of each one of these segments. What's next? Next, I'm going to come up with a small force. The force is going to be equal to 2117 psi times the height, 4 inches, times the width of the beam. With that, I'm going to have here one force, one force, one force. So I need to come up with all of these forces for the stress distribution. The easy way to do it is to put it in the table format. Like in here, in this table format. This table is measuring the distance from the bottom. Here's distance from the bottom, 0, 4, 6.35, 8, 12, all the way to 40. Which means this one here. Look at this. This means the height of the segment. The section width here is actually going to be based on the beam. Let me take you back here to your beam so that you know how the section look like. At the bottom is equal to 18 inch. And here maybe about 18 inch. And here's going to be 6 inches. And here's going to be somewhere in the middle, right? So the width of the beam is going to be different at each height. Let me show you this back again. Here's the width, 18 inch, 18 inch is going to start to drop 6 inches. It's going to start to grow back again. So, okay. The stress all the way in the top, it was tension of 409. All the way in the bottom, it was negative 2250. Now I need to find out the stress. If this is going to be called D distance, it's going to be D minus 2 inches. Why minus 2 inches? Let me take you back here. Because I'm trying to find out this. This is going to be at 2 inches. So this is going to be 12, like D minus 2 is going to be at 10 inches. It's going to be 24 minus 2 is going to be at 22 inches. Just find out the stress distribution. I said, okay. Let me show you also this. So what's happening here? For each one of these segments, I need to find out some forces, right? This gives you the force that we need to work with. Find it. Just find out all of these forces. Back to the table. So now I have the stress distribution. Not right at this point, but actually it's going to be at the mid height of the segment. Okay, so what's next? Find out the force. How can you do this? I know the stress. I know the height of the segment is going to be 4 inches. I know that the width here is going to be 18 inch. So I should be able to come up with these forces. These forces is what I'm pointing here at. This type of forces, small forces. Now, how would you find out the moment for segment? How would you find out this moment distribution? The easy way, you come here, right? Come here at the bottom. You cut a section, you look up or down, which means like, if you remember for beams, we say right or left and take the moment. When you cut a section here, nothing on the bottom, so it's gonna be equal to 0. If you move this to here, this is gonna be your section, right? Because look at this, moment here is gonna be equal to 0, right? If you like to increase the moment or to go to the next step, you're gonna be doing it here at 4 inches. What you can do here, you can look in the top or the bottom. So I decide here to look at the bottom. Can I have only one force? And the force is gonna be right here, this force here. I can call it here F1 if you like. It's gonna be F1 times 2 inches. It's gonna give you this moment value. See this moment value here to there is gonna be equal to this F1 times 2 inches. How about the moment from the top? Let's say I decide to do it from the top. I don't want to do it from the bottom. I'm gonna say, of course, you're gonna have a small forces. Take your section, right? Let's say you cut a section right here. The force on the top here, the tensile forces, is gonna be coming this way. Compressive forces here is gonna be coming this way. So when you cut a section right here, let's say that you're interested in the moment at this location. You say this moment times this moment arm plus this moment force times this moment arm minus this force times this moment arm and so forth. Find out the moment distribution. This is how we have this moment distribution. Now, you're going to have one force that acts against you, which means this big force that you need to consider. Because this point load here is in equilibrium with this stress distribution. So you need also to include it in your analysis. You need to include when you take the moment. Unless you're cutting a section and looking only up. But if you're going to be cutting a section here, looking at the bottom, this force is not there yet. But once you go above 6.35, which means here, this force needs to be accounted for. Now you need to bring this in your analysis. In this table, they split this force into 2 columns. And then at the end, you just add them to come up with the final moment distribution. So this moment distribution, column 7, represents this moment distribution. Okay? Your next step is to take the maximum moment. Now look here at the maximum moment. Where's the maximum moment? I'm trying to figure it out, right? Maximum moment is a 0.75. Where's the 0.75 times 10 to the 6? You can say it happens right here. Here's the 0.75. This one. Which means it's going to be this moment actually. It's going to be your maximum moment. And then you can use it in your analysis. Now, in this table here, for each one of the steps, you have detailed analysis how it is done. So for example, it says here M at C4, M at C8. What does it mean by that? It means moment at this location. Right? Moment at this location at C4, finally is going to be the 0.75. And it shows here how it is done, which is this 0.3. How we came up with this 0.3. At 8 inches, it shows you also how we came up with 112, right? Look at this, 1.12. Just give you this 1.12. And then you add the effect of the pre-stressing force. At the end, is going to be 0.62, which means this, hold on. This 0.62 and this is going to be 1.112. So this segment, MC6, is going to be the what? The 1.12, which is going to be this value here. And from MP, from PI itself, from the pre-stressing, is going to be negative 0.62, right? You add them to each other, you're going to end up with 0.5. I guess I'm going to stop here. I'll let you go. And what I need from you, please, for next time, I want you to read this carefully. Try to understand how this moment is done, because actually you're going to be doing it in your project. So I want to be sure that you understand how this is done. Did you guys see the project submittals needed from you for this coming time and the following?
Yes.
So actually, this method is not needed for this coming week submittal, right? It's going to be for the following. So I want to be sure that you guys, you're able to put this in kind of a spreadsheet and start to do it on your own. The easy way is just take these numbers from here, from this example, and solve it so that you can use it in there. So be sure that you put this in the spreadsheet and you verify your numbers in the spreadsheet, right? So that when it comes to your project, you can just use the same spreadsheet. It's kind of calibration to your spreadsheet before you start to do your submit. Let me know if you have any questions. Otherwise, please sign out. Just type your name in the chat room and see you next time. And you guys have a good night.
Have a good night. Thank you, Professor.
Thank you. Goodbye.
Professor
Have a
Schuster,
good night.
Professor. Hello, Professor.
Yes, you have a question?
Oh yeah, I just had a quick question. So you said this table that we're going to be using for our project, is that for the approximate method? Because that's what project submittal 4 says. It just says precast post tension beam using the approximate method. Will that be using this table?
No, this is going to be the linear elastic.
Okay.
This is
So
the detailed method.
So that submittal isn't up yet, right?
No, it's not there.
Oh, got it. Okay. Just want to make sure. Thank you.
Goodbye.